specific kind of watershed. I will not go into detail here, but there is theory behind. Okay, so you can do some kind of saliency maps with the strategy I presented before, because you want to preserve blobs or remove blobs, whatever. You do that according to a criterion that was the altitude here, or the height, the depth of a basin. So the depth is a second criterion. You can see how long an object is persistent, and you can stack the contour of the object, and you have a summary of your hierarchy. And you simply weight the object's contour with the maximum persistence of the contour it belongs to. So, okay, here is an input image. Here is what you can do with the energy functional I've shown before. You can see that the three most visible contours are the one of the cars, military cars here, trucks and cars. You're missing here one part of the roof of this. It's not present here because it's too close to the background, but you have most of the cars anyway. Okay. So, some illustration. Okay, this is a leveling. I have a very simple image, which is nice to illustrate because it contains round, long object, round object, long object, and also you have white points here in the dice. And what else? Okay, a lot of stuff, but anyway, with a criterion, for example, filtering with round objects, it's easy. You just apply the strategy I've presented just before, and what you get is the long object, the one that are not round. Easy. If you make the difference, you obtain the round object. Okay, there is some objects that are less or more or less round than the other, but you can filter out what you want from the image. Okay, some beginning, not a full application, but just an illustration of the power of the method. To blood vessel segmentation in retinal image, we use the grid channel, first a black top hat transform to make the image straight. Then we apply the strategy, upper leveling based on circularity, and you just the connected component that stay at the end are the blood vessel. There is an available test base available online that is called Drive, with available ground truth, so you can measure how well you perform. And there are the performance measurement at sensitivity and specificity based on true positive and negative rate, accuracy, the rate of pixel correctly classified, and kappa value, which is a statistical measure of agreement between raters. Okay, so here is the first color image. You can look at the green channel that preserves most of the information. You make a black top hat, and you do a leveling on this image, and you obtain this kind of segmentation, which is very close to the manual segmentation. Okay. So here are some more examples, more or less difficult. You can see that there is the yellow spot here that is a bit disturbing, but basically these results look like they are a good step in the right direction. So you can have some measurement in black, in bold. This is our method, but there are plenty of others. And with a simple, very simple, now that you've understood it's very simple, simple filtering step, you can obtain something that is very close to the best results that are more complicated. The most advanced method in this area use a number of other steps, but here it's just one filtering step that gives you a result that is usable, at least. You can see that you're below the expert, of course, but not so much. Okay, the nice thing is that it works in 3D also. You can extend that to 3D. So that first result, we are trying to do that to the same kind of process to segment coronary arteries in 3D. And with a simple filtering step, you obtain something that is not so bad. There are a lot of works behind, but this is a very promising first step in 3D. Okay. Another interesting point is the following. This is a detail, a crop of the first image I've shown at the beginning. When you have an image with two round blobs here, and you want to remove blobs, to preserve blobs, round blobs. Okay. This is the curve of the circularity, the evolution of circularity, starting from two different pixels, one in each taken here, one taken here. And you can see that the curves behave more or less in the same way, but they are not at the same level of circularity. So if you take a threshold, you can find on the blue curve, the spot you're interested in, the node you're interested in, but you have to take all the red curve. You cannot choose in the red curve. And that's the problem with thresholding. If you do thresholding, if your thresholding is not local, you have a problem. It's well known in image analysis. It's also true here. So if you do shaping, you choose this minimum and this minimum. B here, for example, correspond to this node, C correspond to this node, D correspond to this white spot here, and C correspond to this blue spot. And so the shaping I think, yeah, this is reversed probably. Yeah. So you can remove more or less detail, yeah, if you, according to what you want to do, if you want to preserve B or not, or okay. So here are some results with different parameter setting. The image, a shaping based on first attribute, and two thresholds of the same attribute compared to the shaping. So what can you see, what can you notice on the image? Yeah, sorry. Is that in the background here, with thresholding, you have a lot of noise in the background that you don't want. Here you have less noise in the background. Well, it's also true within the shape themselves. For example, this shape is missed with a low threshold. You have it with a higher threshold here, but you have more noise in the background also. So here it's a compromise between the two, and the result is not so bad as a first filtering step. Well, it's easy. A nice thing in the process also is that it's very easy to use any kind of attribute. So here it's two different roundness attribute, and you can go a bit further and obtain a cleaner image by using different roundness attribute. Yeah, circularity and the first two I've shown in the beginning that measure how round a shape is. So this is a very clean result here. Okay, here are some result of using the energy. Within red, the object detected. You can see them. You have seen them on the saliency map, but here you just take a threshold of this tree, and you obtain 3 regions. That's what you want, the most salient one. Okay. You can do object detection also, simply using the attributes, the roundness attribute. In red, this is based on circularity. In green, it's based on inverse of the elongation attribute. But you locate your objects and you can classify them using this kind of filter. Okay. Here is another example application, which is the optic nerve segmentation, the disc you find in the eye. This time we use the red channel because it's there that you find the information. A small closing by a disc, then the tree of shape with a specific attribute, and you just found the best fitting ellipse. It will give you the disc. There is also a database on which you can evaluate the result according to discrepancy. But here the kind of result you can obtain with a disc here located in which is very close to the manual result here on this example, of course. Here are some more examples. The discs are good here, but the method is not always good. Here are the result of the evaluation. You can see that we are better than some of the method, but lower than the 2 best methods existing on the market. But once again, this is a simple filtering step, and I think the result can be enhanced by using more processing step. In the other method, they used anchor points, and based on those points, they do some other stuff. So I expect that with the image filtered, in which the result is there, hopefully, it's easier to apply more post-processing step to obtain better results. But here, we stop just here. Well, there is the accumulated discrepancy, but I will not describe that. Okay. What else can we do with that? 2 more examples I will describe. If I have time, yes, I do. The first one is image simplification. It's not filtering, not exactly filtering. You start from a given image and you just want to obtain an image that is a simplified version of the original one. So you can start with the cartoon model, in which you measure the variance and the length of the perimeter. And you have a parameter nu here, which measures the simplification level. And actually what you want to do is reverse the equation, extract nu, and so you can build the tree of shapes, weight each node with nu that you can compute by reversing the equation, and computer saliency map, which provide you a hierarchical simplification. This is very fast, and this provide very good results actually. So is an original image. You have the saliency map in which you can see that the contours of the original image are preserved, and here is just one level of simplification close to the original image but with much less detail. Some other examples. Once again, this is a choice between all the possible levels. How can you do the choice? It depends on what you want to transmit, for example, bandwidth reduction. Here is image of a bird, in which you have a simplified version which is not so far from the original. Here this image I do like the saliency map of this one. It's very pretty, I think. Like a drawing someone will do manually. But then again, the simplified version is simplified, but you lose some texture information, but okay. Well, we haven't evaluated this method yet. I don't know exactly what we can measure on that result, but we'll find something to assess the quality of the result. Here it's a complicated method. You lose completely the texture, the lines here, but basically you found the two regions. And you can do the same on the military image. Here the saliency map is quite different, but you obtain a good simplified image which contains what you want exactly. So you can post-process this image also. Okay. Another example is a classical algorithm. You probably know this algorithm, this Wenzel-Schwab and Utelencher algorithm. I'm so difficulty telling the name of these two people. Well, the algorithm is very simple. They compute a minimum spanning tree of a given dissimilarity, which is yeah, it can be a simple gradient, for example. And for each edge of the maximum spanning of the minimum spanning tree, they look at the region that contain X, the region that contain Y, and they merge the two regions if this rule is satisfied. So basically, here it's a measure of how the contrast inside the region. Here it's the number, the size. So you don't want big regions, and you don't want them to be too contrasted. There is too much contrast in the region. Well, this method is well known, very popular in computer vision. The problem is that K is not a scale parameter because it violates, for example, the causality principle. I mean, when you move K, you don't control whether the number of regions goes down or goes up. You don't know. So when you change K, you can have very different results, and it's difficult to set up the correct parameter for the method. But it works well once you have set up the parameter. It gives you good regions. So you can make K, transform K into an attribute by reversing the formula. It will give you that max of the difference of this formula. Okay, whatever it is, it's not very important. But it's the same attribute, same formula. So you can plug it into the framework, and here you have a hierarchical method. So how do you do that? You just compute a minimum spanning tree of a distance between pixels, a color distance or a gradient distance. You build a minimum spanning tree that is a hierarchical transform of your image. You have ordered the pixel according to a tree, to a hierarchical tree, which is the minimum spanning tree. For each region in this hierarchical family, you compute K, and then you compute the saliency map, and okay, you can evaluate. You can evaluate because there is an evaluation provided by Arbelaez, which is a collaborator of Malik, and they provided some way to evaluate hierarchical methods or segmentation method. Actually, it's very critical. There is a lot of critiques that can be formulated because it's very hard to evaluate segmentation. But anyway, this is they have provided something so you can look at the results. So it's on Berkeley. I don't remember if this is from Berkeley, I think. You can look at the saliency map of the FH criterion and choose a number of regions. Okay, that's more or less what we did with Fortune. Okay, another example. You see that the most important lines, contours, they are present in the image. And if you choose correctly a good level, you can find the object of the scene. Here is the bird example. Okay, so here is the first result of the evaluation. They have to be taken with care because there are a number of parameters that can be tuned here, meaning that, for example, the first one is on which energy, on which distance are you computing the first minimum spanning tree. You can make a Gaussian convolution on the original image that give you one parameter. So there are a number of steps, but anyway, the FH method give you this result here, and our result with the same method is better. I'm not sure. Well, once again, this has to be taken with care. For information, I've added another method for transforming this method into hierarchical approach. This has been done with Silvio Guimaraes and colleagues at ESIEE. So this is for advertising. Here, Silvio just spent 1 year at ESIEE, and we have worked together. So you are welcome if you want to come. But once again, the evaluations are not definitive. So maybe this method is better. Maybe we're not completely sure. But they can be evaluated. So, some conclusion. Well, this is a new filtering that unlock one of the difficulty of previous connected filters. In previous connected filtering strategy, you had to use an increasing attribute or to do some kind of thresholding, which is not satisfying. Here, by transforming your image, you start from an image, you just transform it into another graph, and you apply morphology on this graph. Whatever it is, here it's trees, and you deal with the graph and you transform it. You can do whatever you want simply by changing the space you're working on. So we have seen two applications: object filtering, which is a generalization of the state of the art, and which allow us to propose new kind of filters, based on shape-based leveling and morphological shapings. We have also done some application to object detection using context-based estimator energy or specific attributes that are designed on the fly. For example, the attribute for the optic nerve segmentation, it's something like it's more or less round, it's more or less in the center. Those kind of information that can be put into the energy and look at the results, very easy. And you can assess the quality, the robustness of the parameters, building a saliency map to see if by changing more or less by tuning differently your parameters, the method vary a lot or not, so the robustness of the parameter can be seen on the saliency map. So basically this is what we've done in this work. There are a lot more things that can be done, especially looking at different attributes. What's the difference between the attribute on the first tree or the attribute on the second tree? Something that I find very promising is to learn the attribute. Here we use for roundness some very classical measure, but maybe you can learn what is round from examples. And in that case, it's totally automated. You don't choose, you just learn to choose the right curves. Maybe also there exists different strategy for dealing with the second tree. And so this has to be explored. we want also to study more mathematical properties of the morphological shapings, see exactly how they can be characterized, and use the saliency map. So, well, since I have a bit of time, I will show you a short demonstration just after this last slide. This slide is for advertising. Once again, there exists a very good book that has been edited by a colleague and myself that does not contain this kind of stuff, of course, because this is very recent, but it's contains a lot of things on mathematical morphology. And it's by with ISTE Willet. There are two kinds of software that you can download and use yourself. They are open source and available online. The first one is PINK, which PINK is the acronym for Pink is not Chorus. For those of you who knew Chorus, it's recursive acronym. So in PINK you find all the algorithms that have been developed in the last years, in the 20 last years at ESIEE, except maybe what you found, what I presented today. What I presented today is, you can find that in Olena, maybe not yet, but in the next release. Olena is a generic environment, generic image processing tool that is developed by Thierry Géraud at EPITA, at the LRDA. It's genericity. What is the meaning of genericity? Well, you all know what an image is. An image can be seen as a graph. You have neighbors. But when you want to, for example, pass from 2D to 3D, you have to write again all your algorithms. It's very difficult to change something. Well, in Olena, everything is written in a kind of using template, kind of template adapted to image processing. And so the compiler does the job for you. Once you've described what a neighbor is, you can work on any type of graph, and the compiler will translate what you want into the code you would have written by yourself. So it is very efficient, very, I mean that you can obtain the same speed as with the original, if you write a dedicated code. If you give to the compiler enough information, for example, you work on a 2D grid with 4 neighbors, the compiler will provide the right code, but it can also provide the code to work on a generic graph. And what I've shown here is I have applied the mathematical morphology on a generic graph. Actually, I built the first graph using a dedicated algorithm on, for example, on 2D with 4 neighbors. But then, if I want to work on the tree produced by the first algorithm, I have to program everything again, but not with Olena. I just compile a new stuff and you apply the algorithm. You don't have to write anything. So you can, these two, there are more algorithms here, but this one is more promising. They compete together and they are developed by different people, but I'm involved in the two teams, so okay, we'll see. And just for conclusion, let me see a very simple example. The screen is too small, so you don't see. Actually, here there are a lot of attributes, and when you click on one point here in the image somewhere, you have the curve of the attribute from the root, from the pixel to the root. So this is very convenient to choosing what kind of attribute you want, or the parameter. I will show you that. This is an X-ray image, and actually they are, the person that undergoes X-ray has a lot of things inside the body. I don't know exactly what they are, but they are left by the doctor, so I suppose they are useful for living. But that's rather strange to have that in the body. But anyway, here this is the tool of that something that you may want to extract, for example. So you can click here, and inside, this is inside. Just go a bit inside here, just to be sure. Maybe more. Okay, I click here. In the, and then you can look at the component here. The component here, this is exactly what you want. So you can estimate from here the depth of here. It's a very simple energy. It's the gradient along the contour, the mean of the gradient along the contour, and you can see that it works very well here. Here it's the ratio. The ratio here is good also. You can see very quickly you obtain the more stuff, but basically here the other, some of the other attributes, they don't work so well. Of course, you don't. The circle here works, but it's a maxima, it's not a minima, so it's very strange. You can't use that. The RR is not working, so you can tune your parameters using that kind of interface, and then produce the whole filtering. Of course, you will obtain when not only this object, but other objects. So you have to be careful. But actually, you can see how robust or not. I'm not in the right place. How robust or not the energy is. So here the deepest minimum is this one. It marks all here, but actually you